Hi, everyone. I'm hoping that yesterday's topic, our last topic in terms of simplifying radicals, has gone well, and we're very, very comfortable to be able to go through and simplify an individual radical. Today, what we're going to do is we're going to kind of take that next step, and you can tell from the title, what we're going to get into now is operations with radicals. So really all we're going to do is we're just going to go back and deal with adding, subtracting, multiplying, dividing, squaring, any sort of operation that can come up with a radical. So to start things off, I just want to walk through the first two that you see on the screen right now. So I'd like you to go through and use any background you have to be able to go through and simplify those two expressions. Okay? Pause the video now. Okay, we're back. So I would have expected an awful lot of people to say that I can calculate the first root, I can calculate the second root, and now just multiply my integers. So I would have expected a ton of you to have 12 and that red solution written on your page. Now, I think it's important for us to note, though, that we could have also tackled that problem a different way. Now, as I put down that different way, I think it's important for us to recognize that really what I've just done in white, that original expression, could have also just been yesterday's topic, but backwards. Notice that if I wrote down my blue, root 16 times 9, I could then take the individual roots of its factors. Now, it requires a little more work, so by no means am I saying that the blue was a better approach. I think we can all see that the red is much more simple. But it's important for us to be able to recognize that we have the option. Remember, we're coming back to revisit that when should I do something versus when can I do something. So I would hope that I saw the red on most people's pages. Let's take a look at B, and maybe we can see that we could tackle that one in two ways as well. Similar to A, I would have hoped that most people would calculate whenever they can. Square root of 36 is 6, square root of 9 is 3. Calculate. So again, I would hope that I would have had a bunch of people give me the red. However, we should also be able to see that I could have taken the square root of the whole term. And again, we're just revisiting a topic that we discussed in previous days. And so now I could do the division operation first and then finish with the square root operation. So I just want us to notice that the blue solutions for us were kind of like the old way that we tackle something. That is, I actually gave you an expression that looked like that in previous days, and I gave you an expression that looked like that in previous days. And we then use that to actually generate our ability to be able to solve or simplify for those white expressions. So I don't want anybody to think like, hey, what's going on? Are we going backwards? We're not going backwards, but what we're kind of doing is stepping back, and we're really examining or opening up our options when we have to deal with operations. So I'm just hoping that we have the red, we can now recognize the blue, and let's kind of address our first piece of theory. So I'm going to give you a second to get that down. And all this is our theory to be able to multiply and divide radicals. So you take a look at the first bullet. And there is our stated theory. It's really what we just did on the previous screen in blue. If I am going to multiply two radicals, then I could multiply the two values underneath my root, and then take the square root of the whole thing. And so what we see on the first bullet then is if I have a root times a root, then maybe I choose to do the multiplication operation first and the root operation second. And that's what we see when we see root AB. Now, you may be asking yourself, why would we ever do that? I think we're going to see some instances pretty quickly where we need to. Now, what you'll also notice in purple off on the right, we need to get down some restrictions. Just when we state our theory, it's important for us to recognize that I can't just plug in an A and a B and assume that they're universal. What I have in red is generic. It's nice. We didn't put in any specific numbers, so we're not nailing it down to anything specific, but we do just have to recognize that, well, even though we've used A and B, there are some restrictions on those. And I hope that we can recognize that we need both our A and B values to at least be 0 or positive to be able to calculate each individual root. So notice my A value has to be greater than or equal to 0. Notice if I had the square root of a negative number, I clearly can't calculate. So you take a look at that next bullet then, and we're going to jump in on our division. We should be pretty good to have taken example 1b, and now we can draw the conclusion that for us to be able to go through and deal with that statement, root AB, all divided by root A, we should simply be able to say that it's equal to root B. It might be a little tougher for us to see it. What we had in that middle step on those blue lines would have been this. We then would have looked at that and said, oh, okay, so now my A's divide out, and I'm left with my B underneath the root. We should be good, though, to draw that direct conclusion that the root of AB divided by root A, I can divide out my A's and go straight to root B. Okay, what I'd like you to do, I want you to take, 15 seconds. I want you to write out the restrictions in that case. Okay, pause the video now. Okay, we're back. So, I'm hoping that we all have this. Now, I want you to just take a close look, because I would bet that I would have had a bunch of people that would have simply copied down our restrictions from the previous problem. Not like you blindly copied them, but you kind of looked at it and said, okay, so for each individual root to exist, what's underneath the root has to be 0 or a positive number. And so then we go, well, A's got to be greater than 0 or equal to, and B's got to be greater than or equal to 0. Except, take a look and see, our A is actually on the bottom of a fraction. And so we have to be very careful that if we allowed A to equal 0, then on the bottom of that fraction, we're going to have the root of 0, 0. We get an undefined value again. So let's be very careful on that then, and make sure that we note that the only thing that A can be is a positive value. It cannot include 0. Okay, there's our theory that we're starting off with. So for us to work our way through now, all we're talking about, can we multiply and divide radicals? So let's get some practice doing it. Okay, so I'd like you to take a look at problem 2. We're going to have a new section of our problems. Same instructions, simplify. And I'd like you to get down both A and B. And I'd like you to give each one of them a shot. So now that we've dealt with walking through, multiplying, dividing radicals, I think we should at least be really comfortable on A, and then maybe B gets a little more difficult just because of quantity. So I'd like you to pause the video right now and let's give A shot. Okay, pause it now. Okay, we're back. So pretty quickly, I'm hoping that we can see that really all A says is take 3 of something and multiply it by 2 of something. And so we're going to end up getting 6 of whatever those somethings come together. So the fact that really all we talked about in our theory was how do we multiply radicals, that we see coefficients on those radicals shouldn't be a big addition to this problem. So for us to go through, I have my 3 root 2 times my 2 root 7, multiply my coefficients, 3 times 2 is 6, and to multiply our roots means multiply the numbers underneath. There we go. Hopefully we got down to 6 root 14, and hopefully we felt pretty comfortable with it. Okay, I'd like you to work your way through B now. So we should have B down. If not, copy it down now. Let's pause the video and get a solution for B. Okay, pause it now. Okay, we're back. So now that we've tackled A, I would expect a bunch of people to have something that looks like this. Like almost like, okay, so I'm going to multiply my coefficients. We hopefully didn't write down the times by 1. And then I have what I have underneath my root. So my 6 times my 10 times my 15. Now, I'm actually hoping that we didn't write down any of that, but instead we just calculated as much as we could. So our 5 times our 1 times our 2, there was a 10. Well, my next numbers get a little bit big. So like I've got 60 times 15, or I've got like 6 times 15 is 90, multiply that by 10, 900. We get something pretty big. Okay, now we should recognize that we're going to have to reduce that. So this comes back to one that we tackled from yesterday. So what I'd like you to do is pause the video and see if you can reduce that radical. Pause it now. Okay, we're back. So if we didn't know that 900 was really just 30 times 30, say we didn't know that, then what we could do is we could just go and say, okay, I would at least hope that we said like, maybe like 9 times 100, maybe. And so we could at the very least say that we had our 10, the square root of 9 is 3, the square root of 100 is 10. Calculate that, and we should get down to 300 as our answer. Okay, so hopefully for us, going through and multiplying 3 radicals together wasn't that big of a deal. Okay, all I'm going to do is I'm going to erase a little bit of that because I would hope that really you guys could just show me the red answer. I would be totally fine with that as your solution. Don't ever feel like you got to show me the gold. And if you happen to not recognize that as a root, no worries. But it's important for you to know that you don't have to do a factor tree for it. Okay, what I want to do is I want to go through B, but in a different way. Now, the first thing I'm going to say is I'm not recommending this as a means for everybody to use. I'm going to argue that that gold method, that's your blinders approach. That's you just saying, okay, I'm going to multiply all my coefficients, I'm going to multiply what's underneath my roots, and then I'll reduce as what I need. However, if we start to look at this problem a little bit like fractions, multiplying fractions, that rather than just blindly multiplying to produce the gold and then having to work our way down to simplify to get the red, maybe we could do like a little cross reduction where we do a little bit of simplifying first. This is going to have the same sort of feel. So I want you to see what I'm going to do in my original problem. I'm going to go through and I'm actually going to do little factor trees for each value that's underneath my root. Now, the reason I'm doing that is so I can see what's going to make up everything underneath my root. Okay, I want you to focus in on the green because I'm still going to do this. Well, what do I have out in front? Well, I have a 5 times a 1 times a 2. Okay, I can stop writing down the times the 1. We're at least pretty good with that. And we recognize I got my 5 times my 2. Now I'm going to move underneath the root. But before I just blindly write down my root, I'm going to see if I can simplify anything in one go. Okay, I noticed that I have 2 2's here. That when I multiply that stuff together, I will eventually get 2 2's underneath. So, take the square root of those 2 2's, and I get 1 2. Well, now I can do all that simplifying. I see that I have 2 5's. So to take the square root of 2 5's, I got 1 5. And I also see my 3's, that when I take the square root of those 2 3's, I get 1. And I notice that everything had a pair of factors that was underneath. So now all I have to do is just calculate everything. Okay, well, I've got a 5 times 2, that's a 10, and another 5 times 2 is another 10, and then multiply that by 3. Hey, look, 300. And maybe I do a little reducing first. Okay, I am not saying that that method is for everyone. However, I'm going to argue that if you get a little good, if you get a little bit of practice to feel comfortable with that gold approach, then I would ask, maybe pressure yourself a little bit to try the approach I just showed. See if you can work your way through doing a little reducing first. I think it can really speed up your process. Okay, let's jump in and play around with a few more problems. Okay, so let's take a look at the screen and what we have now. You'll notice in part C, we've got one that looks an awful lot like B. So what I'd like you to do, pause the video and let's use C as a gauge of how comfortable we feel going through. Okay? Full solution to C. Let's pause the video now. Okay, we're back. So, if we put on the blinders a little bit, and I would argue that's okay right now, like we've really only done one like this before, then our calculation should have been 6 times 5 times 2, multiplying all of our coefficients, and then 3 times 6 times 10, multiplying everything underneath the roots. That gives us, well, 6 times 5 is 30, double it is 60. Underneath, I got 18 times 10, that's 180. And now I'm on the process of going through and reducing. And so maybe then we've got our little factor tree. And maybe we're saying, well, that's an 18 times a 10. That's a 9 times a 2. That's a 5 times a 2. Now I'm done my factor tree because I can see that I'm going to have 60. That was out in front. Square root of 9 is 3. I also notice that I have 2 2's. So the square root of 2 2's is 1 2. And the only thing without a pair is my 5. So I just need to put that together. 60 times 6 is 360, root 5. I would have expected an awful lot of blue solutions. Okay, what if we tried to do a little bit of reducing first, though? Okay, my factor trees, I can't factor 3 any further, it's prime, but I can on 6 and I can on 10. So for me to go through and put that stuff together, I'm going to have my 6 times my 5 times my 2, and now underneath my root, I notice I'm going to have 2 3's, so I can take the square root of those 2 3's, which is 1 3. I also notice that I have 2 2's, so I can take the square root of those 2 2's, so I have another 2. And the only thing that doesn't have a pair is that 5. It's left underneath. And now I can put all that stuff together. 30, double it is 60. Multiply by 3 is 180. Double it, 360, root 5. So there's both approaches that we've seen. Hopefully we're comfortable at the very least with that gold to blue transition. And with a little bit of practice, you can really get quick with the red one. Okay, now I'd like you guys to jump into D. So we haven't really done a problem that looks like D yet. I'd like you to go through and try to use any background you have to get a solution to D. Simplify D. Okay, pause the video now. Okay, we're back. So I'm going to produce maybe 2 solutions to this one. And I don't really know if there's that much of a difference between the two solutions. Like, I think one's better, but I could be won over to either argument, that they're pretty equivalent. I think my first thing that I would do if I was to tackle D is take a look and see, can I just do the division? So in that case, I notice, well, what I end up having then is my 15 divided by 3, those divide evenly. So there's a 5. And now my root 20 divided by root 5 is a root 4. Now, just be very careful that there's some times when people put an idea in their mind where they go like, yeah, but wait a second, like how many times does root 5 go into root 20? And they focus so much on the 20 and the 5 that they want to answer 4. And we just have to be very careful here. If root 20 divided by root 5 gave you 4, then that means that 4 times root 5 has to give you root 20. And hopefully we can see that isn't the case. 4 times root 5 is 4 root 5. So let's just be very careful with that. If we have our focus, then we come down with the red, which is pretty good. And we can see that we need to calculate our root 4. And obviously you wouldn't have to show me that line. So we come down with the red solution, probably pretty straightforward. An alternate way, though, might be that maybe we focus in on simplifying individual roots. Like maybe our instinct kicks in and we already are able to notice, hey, wait a second, root 20 isn't simplified. And maybe our focus becomes, well, let's reduce each individual radical first. So maybe on top, I'm going to take my 15 and then take the square root of 4, which is 2. So I get 30. The 5 is still underneath the root. On the bottom, I can't reduce that one. But now when I go through to examine, my 30 divided by 3, that gives me my 10. And now my root 5s divide out. So I hope you can see that, like looking at the length of each one of those solutions, they're equivalent. So I wouldn't necessarily argue that one was more efficient than the other. If I had a choice of method, though, I would be following the red. I think if I can do that division and make things smaller, I'm going to try to eliminate the fraction, the division first, and then maybe reduce anything that I have afterwards. But you see, hey, it's your call. So we come back to that question of when can I do something versus when should I do something? Okay, let's jump in and play around with a few more. So let's focus in on that division. I'd like you to give it a shot. So all I want is one possible solution. You go through and you solve for E. Okay, pause the video now. Okay, we're back. So I take a peek at this one. It should be pretty straightforward, I would imagine. Your 18 divided by -3, that divides evenly, so that's going to give me a -6. I then have a root 24 divided by root 8. That is going to be a root 3, and I am good. Nice. Hopefully we match up. Okay, I want everybody to go ahead and tackle F. So pause the video now. Okay, we're back. So the first thing I look at is my coefficients. 4 does not divide by 3 evenly, so I'm not going to try to divide those. Also, I notice root 90 does not divide evenly with root 72, so I don't think I would deal with that either. Now, I could look at my root 90 and my root 72, and I notice that 9 goes into both 90 and 72, but that starts to get a little... Okay, I think this would be one where I'm going to take the second approach. I'm going to actually look at the top, and I'm going to say, let's factor my root 90. That's pretty quick. That's a 9 times 10. And so I can simplify my top, take the root of 9 as 3, simplify that with the 4, can't take the root of 10. Now on the bottom, I can deal with that factor tree. Well, that's 9 times 8, but I've also gotten a little bit better, hopefully, that, we recognize that that's also 36 times 2. And so now I go through and I take my square root of 36, which is 6. Simplify that with the coefficient is 18. Now I have my 2 left underneath. And now I come in on a fraction that I can reduce. I look at my coefficients. I can divide out a 6 from both the top and the bottom. So that's going to get me a 2 and a 3. I also take a look at my roots, and now my roots do divide evenly. So when I divide out my root 10 divided by root 2, that's going to give me a root 5. So you can tell me 2 root 5 over 3, or you can tell me 2/3 root 5. I have a feeling more people are going to be comfortable with that first option. There we go. Hopefully we match up, and we're starting to get more comfortable at dividing some radicals. Okay, we're going to keep our practice going. Okay, so what you see on the screen then, problem 3. So I want this to be a different section in your notes. We still have the same instruction. We're going to simplify. I'd like you to get down both A and B, and I would like you to come up with a solution for both. Okay, use whatever you've got in your background to work your way through and simplify both A and B. Okay, pause the video now. Okay, we're back. So I would have hoped that we are going to calculate anything we can calculate. And so we would have ended up getting, well, that's 2 times 4, so the square root of 16 is 4, and the square root of 4 is 2. We probably didn't even write that line down. We might have just said, hey, that's 8 plus 6. I get 14. Now, I'm hoping you're looking at that and you're kind of asking yourself, okay, why are we being made to do this? Like, why are we even spending our time talking about this? And I just want to draw to your attention that since I am adding radicals, if I went to do the same thing as if I was multiplying radicals, well, then I guess I just add the numbers in front and I add the numbers underneath. That pretty quickly you can see that that would give you 10 root 5, and 10 root 5 does not equal 14. And so when we come back to that question of, can I do something? I hope you can see that for us to add radicals, we can't just add the numbers out in front and add the numbers underneath. We can't. We should all be 100% confident in the red. And we recognize that that blue is not an option. So I'm going to erase that before we even put that in our mind. Okay, I can pretty quickly go through B now because we should have had the same approach. It would have been a 2 times 4 minus a 3 times 2. There's my 8 minus 6. We get down to 2, and we can clearly see again that that wouldn't be negative 1 root 12. Like, I don't even have to reduce root 12. We should be confident in the red answer, and clearly it's not going to give me a negative value. So let's get rid of that purple again. So why are we even talking about this in terms of context? I hope that you guys can see that as we perform that addition or subtraction operation, this is going to feel an awful lot like algebra to you, maybe even more so than multiplying and dividing. I'd like you to get on your page in nice big letters. Like versus unlike radicals. Like, that's really what we have here. That if, and you don't need to get this down, but if I was to say, like, let's let x equal root 16. And then let's let y equal root 4. That we should be able to see that what you have up here is a 2x plus a 3y for question A. And like, you can't add those things together. Now, before we kind of get a little confused, notice if I change that to multiply, you can multiply 2x times 3y, but we can't add or subtract it. And so as we work our way through the addition and subtraction operations with radicals, treat them as if they were terms. We can collect like terms. You can't collect unlike terms. Therefore, we can collect like radicals, but we can't collect unlike radicals. I think that does us pretty good for theory for adding and subtracting radicals. Let's just jump right in and get some practice. So take a look at what we've got on the screen. I think everybody should be able to go through A and B super quickly. So pause the video now. We'll check up in the end. Okay, we should be back. So we should have noticed I have two radicals that are both root 5s. So I can put together those root 5s. I've got 1 root 5 plus 2 root 5s. There is a 3 root 5, and I have nothing to collect with the root 6. We're done. Now, in terms of form, there are no rules whatsoever about which radical should be listed first, like a larger number or a smaller number. Who cares? We just want to make sure that we simplify the expression. Okay, we take a look at B, and we should have matched up with B. 5 of something minus 2 of something is 3 of that something. We simplify down to 3 root 3. We are good. So hopefully we match up in both those cases, and we can jump into kind of like the next type of problem. Okay, I'd like you to just take a look at C for right now. And we're going to walk through C together. The first thing we notice is we've been asked to add together two radicals. So we see two operations in the expression, addition and roots. So I'm hoping our instinct would say, well, if we could calculate the root, then I'm going to calculate whatever I can. But we notice that we can't calculate root 20 and we can't calculate root 5. So then we try to do the addition of them. But we notice 20 and 5 are unlike radicals, so we can't add them together. I'm going to bet and say that I already have a bunch of people that are saying, yeah, but wait a second, root 20 can reduce. And so maybe our action actually becomes, let's reduce the radical first. Some of you have had enough practice at this point, you don't even have to write down that factor tree anymore. You can just see it. You can see taking the square root of 4 with the 5 left over. Now that expression just becomes 2 root 5 plus root 5. Well, that's about as easy as it comes. So we have 3 root 5s. Hopefully not too bad. So we've now added in a new strategy. If we can't just collect right off the bat, maybe we can simplify a radical to change it. And perhaps we do have like radicals, we just can't see it. Okay, I'd like you to work your way through both D and E. Okay, again, give them a shot. Pause the video now. Okay, we're back. So as we work our way through D and E, I can't put together those radicals. They're unlike. I can't calculate either of them, but I can reduce the first one. Take the square root of 9, that's a 3. So my first reduces to 6 root 2. Now I can collect. There we go. Hopefully we match up. The only difference when we take a look at E is I can't calculate either root now, and I can't subtract those two things. That rather than going through and reducing one radical, I might want to reduce 2. I just want to shy you away from this strategy, and I probably had a handful of you that did it. You looked at the second radical, and your focus was, how can I make them the same radical? And so what we ended up doing was now saying, well, my first one was a root 12. I can make that second one into a root 12 by saying I have 4 root 12s. Now I can collect. My concern for you is that you're going to get into this feeling of going, okay, now I'm done. And we move on to the next problem. And we don't focus in on the fact that root 12 can be reduced further. So my advice to you would be, when we go through, if we recognize that we need to reduce a radical then just reduce every radical. Break them down to their bare bones. Reduce them fully. Then start to compare your radicals. So my suggestion to you would be, okay, there's a 4 and a 3. We probably aren't even doing the factor tree. We can already see it. The next one, we probably still are. However, I would at very least hope that we've gotten a little more efficient at recognizing 48 under a root as 16 times 3. You now take that. Square root of 16 is 4. And now we can collect. And notice that is your root 12, but we're fully simplified. It's not that my green solution would have been more efficient than my previous solution. It's just that now I know that that final radical is fully simplified. I'm ready to leave the problem. Okay, hopefully we match up in the end. That's going to give you some great feedback in terms of how good we are with now multiplying, dividing, adding, and subtracting radicals. All we're going to do for the rest of the day is I'm just going to keep throwing more operations at you. So maybe we're going to get a mixture of operations. Some expressions are going to get a little ugly. And by a little ugly, I mean some of them are going to get downright ugly. So what I want you to do is just work your way through and use all of your background now to try to simplify these expressions, to perform these operations. Okay, here we go. So I'd like you just to take a look at what we've put up on the screen. There's problem F, there's problem G. I don't know whether you want to keep going, but keep working through as comfortable as you are, and then what we'll do is we'll keep checking in to see how well we match up. You see some brackets being put in, and of course, anytime we're doing operations, maybe we need brackets to specify which operations are required first. Okay, let's focus in on F. I'd like you to work your way through F. Pause it now. Okay, we're back. So, first thing we should have looked at, can you collect what's inside the bracket? So can you do the subtraction? Quick answer is no. And it's really quick because I see that root 2's and root 5's won't reduce further. So since I can't do that subtraction first, then I'm going to have to do my multiplication first, which means I need to expand that in. So I need to take my 4 root 3 times 7 root 2. That's a 28 root 6. I then need to take 4 root 3 times negative 3 root 5. So there's a negative 12 root 15. I know I'm finished because if I took a quick peek back, I can see that I'm going to have a 3 and a 2. So when I multiply those together, I can see that all I have in there is a 3 and a 2. It won't reduce. Same thing, I see that I have a 3 and a 5. I can see it won't reduce. So I can tell at the very beginning that I won't have to go through and reduce that further, that what I have in red is my final solution. So I'm just going to get rid of those factor trees because they're completely unneeded. Now, if you did a factor tree just to examine it, no worries, but they're not required at all. You give me that red solution, perfect. Hopefully we match up. Okay, we're now good at being able to multiply with some brackets. We're starting to make our expressions a little uglier. I want you to take a look at G. I think everybody should be able to work their way through G. I just think it's going to take us a little longer to do it. So what I would like you to do, pause it now, get an answer to G, and then maybe I'll show you some ways to be a little more efficient. Okay, pause it now. Okay, we're back. So we're working our way through G. This would have been what I would have expected on most people's pages. Okay, I now have to multiply my firsts. So I'm going to have my 8, and root 3 times root 3 is root 9. We're going to talk about that in a second. I then notice that I would have to multiply those outsides. So that's going to be a minus 2 root 6 I then notice that I'm going to have to multiply these insides. So that would be a negative 12 root 6. And then I have to multiply these last terms inside each bracket. And that would be a positive 3 root 4. Okay, there is us going through and doing the multiplication operation. We noticed that we had to multiply first because we couldn't collect inside each bracket. Now we get down to that and we can actually calculate some stuff and simplify some stuff. Notice in my blue term, I can calculate 8 root 9 because that's 8 times 3. Now, you don't have to write that down. Clearly, you could just go through and say, okay, well, root 9 is 3, multiply that by 8, 24. Notice on your middle terms, the gold and the green, those are both root 6s. So we could collect those then. And if we collect those, then we're going to get this kind of mixture of blue and green. Or gold and green, I'm just going to call it green. There's my negative 14 root 6. And now we take a look at that red term on at the end. We notice we've got a root 4. That's my 3 times 2. Same thing again, though. You don't have to write that. If it's 3 times 2, there's your 6. Let's clean it all up in the end and bring everything together to get our final expression. And I'm going to put that final expression in gold because I have my 24 plus my 6, which I can simplify, and I can't simplify it with the radical. I get down to 30 minus 14 root 6, and I think we've done a great job. Now, what I want to talk about is maybe the way we think about some stuff. And I really want to talk about this first line, because I actually want you to go through and multiply those and never, ever, ever have the number 9 or 4 pop up in that line. I'm going to just pull down to the bottom. We're going to walk through this in purple. That when you multiply that first multiplication, the 2 root 3 times 4 root 3, the best way to think about that is this. It's 2 times 4 times root 3 squared. Now, you would never write that down, but that's the best way to think about it. Because you can collect your 2 times 4, multiply that. When you see root 3 squared, we do not want that to be, oh, okay, so that's root 3 times root 3, which is root 9. No. Remember, a square is the opposite operation of a square root. So they just cancel out. We want to look at it that way. So when you get asked, hey, what's root 3 times root 3? 3. 9 never even comes into your head. That's going to make your life so much easier. And you're going to find you get a lot faster with this stuff. So I'm going to get rid of that purple. And I'd like to talk with you about a way we could tackle G where we're about as efficient as we can be. Okay, I'm going to go through the way I would tackle G. I'm going to multiply my firsts. 2 times 4 is 8. 8 times root 3 times root 3 is 3. I'm going right to that. However, I think I can do that all in my head. 2 times 4 is 8. Root 3 times root 3 is 3. 8 times 3, 24. Now I'm going to do my outsides and my insides. Well, if I look at my outsides, I have a negative 2 root 6. My insides are a negative 12 root 6. Well, negative 2 root 6, negative 12 root 6 is a negative 14 root 6. And now that I multiply my lasts, I'm going to have a negative 3 times a negative 1, so that's a positive 3. So I'm thinking this. And then a root 2 times root 2 is 2. Root 2 times root 2 is 2. It's not root 4, it's 2. But for all the same reasoning, we can just jump straight to 6. You clean it up, and you can come in on just the purple solution. And I'm telling you, with practice, you can get there so quickly. Okay, expressions are getting uglier. They're going to get even uglier. Let's keep it going. Okay, I'd like you to take a look at H and I. So let's focus in on H at the beginning. I'd like you to get down that expression, and now I'd like you to go through and fully simplify. Okay, pause it now. Okay, we're back, and I just want to confirm that what you tried on your page was not this. I want you to imagine that that expression was like 7x plus 4y. I don't know, something like that. You make sure that what you tried on your page would not have been this. You make sure that you didn't just go, oh, okay, so I square the first, square the second. Because you know that that red expression doesn't give you 49x squared plus 16y squared. You'd have your middle term in there too. What about the 56xy? I think some people didn't recognize the context of that white expression. That's just a binomial squared. If I was to really simplify it for you right now, I would have bet that I would have had a bunch of people try to tell me that x plus 3 squared equals x squared plus 9. And they forgot that we also have to multiply those together and double it to get our middle term. So if we made that mistake, let's make the correction. And now we're coming along for our solution here. So I think this is actually really good for you. As the numbers get bigger, put in one more line and I think we'll be comfortable. So this to me would be your most efficient solution. Okay, first thing we need to do, square the first. So I square 7 and I square root 3. Notice I went straight to 3. Okay, now I need my middle term. Well, my middle term is found by multiplying both terms and doubling it. So I multiply both terms. So my coefficient would be 7 times 4 is 28. Double it. There's a 56. This is a really common mistake, that we then go root 3 times root 5 is root 15, double it, and we go 30. That is wrong. Notice that if we were to expand the original brackets, we would have had a 28 root 5 plus another 28 root 5. Notice, if we take 28 root 5 plus 28 root 5, that gives us 56 root 5s. Sorry, how about 15s? That gives us 56 root 15s, not root 30s. So we have to be very careful that when we double something, we double the coefficient. So as we think about that, I have 7 times 4, there's 28. Double it is 56. What am I doubling? Root 15s. And now we have to square the last. Square the 4, square the root 5. Notice, root 25 didn't even come into my head. Okay, numbers got a little bit bigger, so that's why we included that line. Now we can just spend some time calculating some stuff. Okay, 49 times 3 is going to be 147. Keep in mind, that's like 3 times 50 almost. So 150, then just take off 3. I can't do anything with this 56 root 15. That's fully reduced. At the end, I've got 5 times 16. That's my 50 and 30, 80. You collect what you can. Make sure everything is simplified, and we are good. So hopefully we match up with what we've got in the end. I think what we've put down there in those 3 lines is a really good solution for you. There's enough written down that we're not risking mistake by doing too much in our head. But we're not blindly writing down an extra line, more work than what's needed. Okay, I want you to jump into I now. So you get down I, give it a shot. Fully simplify, pause the video now. Okay, we're back. Now, here's where I'm going to argue we really have the blinders on. When you looked at those, did you recognize that you have the exact same terms inside both brackets, but with different signs? We've got conjugates, and if we have conjugates, then I know my middle terms are going to cancel out. Now, maybe we put the blinders on and we did something like this. Okay, 5 root 2 times 5 root 2. 5 times 5, root 2 times root 2. And then we went, there's my outsides. So that was a positive 15 root 12. Then we went, there's my insides, a negative 15 root 12. And we didn't really focus in on the fact that those are going to cancel. That's okay. However, I think we really want to just take a quick peek because that can really save your time, let alone risk for mistake. So I'm going to get rid of that because we're going to be as efficient as we can be. The middle terms all cancel out, so now all I need to do is multiply my lasts. There's a 3 times 3 and a root 6 times root 6. Now we can just calculate some stuff. So there's a 50 minus 54, negative 4, and we are good. That one cleaned up real nice. Can I get everybody in their notes? Put a huge star by that one. I mean a huge star. That might come back to help you in the future. Okay. Here is our doozy for today. So what you see in our last one, there's question J. And I'm going to leave that with you because I think if you can go through and simplify J, then there will not be anything in your practice that you are going to struggle with. So let's go ahead, fully simplify, pause it now. Okay, we're back. So hopefully we didn't break bed mass and try to expand in that because we recognize that we have an exponent and we have to do our exponent first. So that means I'm going to leave that 2 root 2 out in front, and I'm going to square my perfect square. Okay, 3 times 3 is 9. Root 3 times root 3 is 3. I multiply those together now, and I'm going to get a 15 root 21. Double it is 30 root 21. Now I square my last. 5 times 5 is 25, and root 7 times root 7 is 7. Now I can clean up what I've got. What I have inside the brackets is going to be 27 plus 30 root 21 plus 175. So that's going to give me that 202 plus my 30 root 21. Okay, this looks an awful lot like a previous problem now. Now all we need to do is expand in that radical. And so my final expression is going to be 404 root 2 plus 60 root 42. And I know that that's my final expression because all I have is a 2, and in that last radical, that is going to be a 7 and a 3. I can already see that this 42 will not reduce. If you got down to that, then I think you're doing exceptionally well for today. You've got everything you need. Job now for everybody is just make sure we got enough practice to make it automatic. Okay, jump in, play around with your practice. Good luck.